Welcome back. So we were talking about basically generative modeling, and we talked about variational inference as an approach to learn unknown distributions, and we saw its connection with supervised learning. We also talked about an elegant idea, generative adversarial networks, that aim to learn underlying distributions and the ability to sample from them by forming a specific zero-sum game. Okay? Now, we want to talk about this connection a little bit more. And to do that, we're going to talk about what we call the variational representation of F divergences. So the main idea is that given that F divergences, notably Jensen-Shannon divergence, that is precisely the objective we use for training GANs, is leveraging some convex function. We can use tools from convex analysis, in particular Fenton duality, to basically show that there is a very nice relationship between minimizing divergences and a min-max formulation, as we saw in the previous part of this lecture. Okay, so we're going to talk a little bit about that, and therefore establish a kind of a connection between divergence minimization as well as the min-max optimization that we saw, and also see how we can generalize the usual GAN that we saw in the previous part to other notions of F divergences. Okay. Right. So our main tool is what we call Fenton dual of a convex function, which is basically defined by equation 8. So there are very nice interpretation of this result and this definition. So it's not too important for us, but let's just take this as a definition. And let's also point out that when I have a convex function and I define this dual, under certain condition, the dual of the dual function will be the original function, essentially. Okay. And also, when the function is convex, the dual of it is going to be a concave function. Now, a main usage of Fenton duality is when you want to solve convex optimization problems. So it turns out that sometimes you can form the dual of your problem and solve that more efficiently. There are also usage of this concept when you want to talk about optimality guarantees for various optimization algorithms for convex problems and also non-convex problems. Okay? For us, we're going to use it to basically show a connection between minimizing divergences as well as min-max optimization problems that are at the core of GAN training. Okay. All right. So what's the idea? So the idea is that we're going to use Fenton duality and in particular this representation to lower bound, let's say, a specific F divergence between distribution Q and P. So it is useful to think of Q as the underlying distribution that we want to learn, the data distribution, and P as basically our parametric distribution, if you will. Okay, so that aims to approximate Q. Okay, all right. So let's see how we can proceed with lower bounding the divergence using Fenton duality. So the first thing you can do is basically just write down the definition of an F divergence. Okay, so this is what we discussed earlier. Then we can plug in what is the function f in terms of its Fenton dual f tilde. Okay. So therefore, nothing complicated here. We just use some definitions. Okay. Then I claim that we can actually lower bound this quantity by essentially changing the order of the integral and the maximum. Okay, and this is actually due to the Jensen's inequality. So max is basically a convex operator. Okay. And Jensen inequality basically is saying that for all convex functions, so let's see if I can write it correctly. So the expected value of f of, let's say, x is larger than f of the expected value of x. Okay. So again, the idea is that if I consider a convex function like this, okay, so the average of basically function values is larger than the function value at the midpoint. Okay, so here is the average of the function value is going to be somewhere here. Okay, and the average at midpoint is going to be here. So this distance is basically saying that this is described by basically Jensen. Okay, so saying that the function value evaluated at the midpoint is smaller than the average of function values. So using Jensen's inequality, therefore, we can establish this result. Okay, and I claim that we can again lower bound this using the fact that the maximum here, which comes from the definition of differential duality, is over all possible t tilde. Okay. Now, if I restrict that to basically a specific, let's say, subset, a specific set of t tildes, then I can lower bound it. Okay, because I don't allow finding the maximum over the entire universe. I just allow you to find the maximum over a smaller set. Okay. All right. Then the last step is also kind of trivial. So if you look at these two integrals inside the maximum closely, there are essentially two expectations. Okay, so one is with expectation with respect to Q, the other one is expectation with respect to P. Okay. All right. So therefore, with just using the definition of the F divergence, the definition of differential duality, Jensen inequality, and restricting the search space that we are dealing with to apply this max operator, we can find a simple lower bound for the F divergence. Now, hopefully, you can see that this will lead to a min-max optimization, because I have a max operator here, and I want to minimize the divergence between two distributions to learn the underlying distribution. So there is basically a min-max optimization at the core. Okay. Precisely like how we train GAN, as we discussed in the previous part. All right. So now let's change the notation slightly. So in the previous slide we had t tilde. I'm just gonna call that d. Okay. So this is going to be our discriminator, and therefore what we showed was that the divergence, the F divergence, is basically lower bounded by the maximum of this the differences between these two expectations. Okay, so I have basically an expectation of d with respect to Q, data coming from the underlying distribution, minus the expectation of this quantity when data is coming from distribution P. Okay, so essentially data generated by our generator. Or the distribution described by the generator. Okay. All right. So now, what's the connection to GANs? Well, so think of Q as your data distribution, and assume that P, the estimator of Q, is basically parameterized by PG for some function gx of z. So this is exactly the generator that takes, let's say, some random Gaussian and transforms that to samples coming from PG. Okay. Now, the task of fitting the underlying distribution, therefore, by minimizing this F divergence, is gonna reduce to this min-max optimization problem. Okay. And this is essentially what we call the objective for F GAN. Okay. So where F stands for F divergence. And basically, this idea shows that shows first of all the connection to variational inference to some extent, and under some restrictions, and secondly, it provides a systematic way to generalize the objective for GAN training to other notions of divergences, not just Jensen-Shannon divergence. Okay. All right. So one basically side note for you is as follows: that you can show that this lower bound that we have here is going to be tight when you set the discriminator to be the derivative of f evaluated at the ratio between Q and P. And for GANs, or for GAN that we talked about previously, this basically will be the ratio of Q and PG, and Q plus PG. Okay, so this is precisely what we saw earlier as the best strategy for GAN when we are using technically the Jensen-Shannon divergence as our metric to fit the underlying distribution. Okay, all right. There's also a nice interpretation in terms of what the generator and the discriminator are trying to do. Okay, when we look at the this equation 10. Okay, so in particular, we can basically think of the generator as trying to obviously minimize the divergence estimate, but the discriminator, what it's doing is trying to tighten our lower bound. Okay, so therefore as we do the training, as these models interact and leverage basically the training data as well as the randomly generated data, as the training progresses, and if our training algorithms are good, we're going to reach the equilibrium such that at the equilibrium, the inequality in equation 10 will be tight. Okay. All right. So this basically again is a very useful and nice result in the sense that it provides this connection between min-max optimization and minimizing the divergences. Also helps us to generalize the original GAN training from Jensen-Shannon divergence to arbitrary F divergences. Okay. Now, a natural question here is that, well, we now found a way to basically talk about generative modeling using various F divergences. But there is another class of distances between distributions, notably vacillational distance. Okay. Can we also come up with a gain formulation if we want to minimize the vacillational distance between the underlying distribution as well as our parametric distribution? And if so, is there any benefit in terms of using the vacillational distance over F divergences? All right. So indeed, that's possible, and that's called the vacillation GAN, a very famous algorithm and idea. So first of all, let's try to motivate why you want to use vacillation distance as opposed to the F divergence. Okay, and the idea is that again, when you look at the definition of F divergence, we see this ratio between Q and P. Okay, and for the F divergence to be, let's say, well defined or bounded and have nice properties, we want to make sure that the support of P covers the support of Q. So that is to say that if P is 0 at some distribution or some areas of the universe, if you will, Q is also 0. Okay. Otherwise, this ratio is not defined, and it's gonna lead to discontinuity in F divergences. For instance, in the case of Jensen-Shannon divergence. Or it could also result in an infinite divergence in the case of the KL divergence. Okay, so therefore, when the distributions, right, that we are using, so the real one and the parametric one that we use to fit that, don't have overlapping support, there is going to be some issues with F divergences. It turns out that that's not the case for vacillation distance. Okay. So in fact, vacillation distances are still nice. So you don't have the discontinuity, for instance, an infinity issue that we talk about if there is no overlapping support. If the supports have areas that don't overlap. So we don't have that with vacillation distance. So therefore, and in many scenarios, it is potentially more useful to use vacillation distance over F divergences for generative modeling. Okay, that's what motivated people to try to not only basically generalize Jensen-Shannon divergence to other notions of divergence and go beyond that and replace the F divergence with let's say vacillation distance. Now a natural question then is, well, with F divergences, we had this game that we talked about, the adversarial game. Are we going to have a kind of similar results if we use vacillation distance as our way to characterize how well our distribution is fitting the true distribution? And the answer is positive. In particular, you can use something that's beyond the scope of this course, but I refer you to materials on optimal transport if you're interested. So we can use Kontrowicz-Ramenstein duality, which in some sense represents, again, provides a variational representation of the vacillational distance. And we can use that to basically represent the task of generative modeling with vacillational distances, again, as a form of min-max game. In particular, if you consider one vacillational distance, which is defined here, you can show that it's going to be written in this form. So it is a maximum, okay? And then if you want to minimize the vacillation distance, therefore we are minimizing the maximum of these function differences, therefore a min-max game. Okay. One catch here, or basically one thing to point out, is that the maximum is over the set of all, let's say, discriminators that are Lipschitz. So in particular, the Lipschitz constant of the discriminator must be equal to 1. Okay. So this in some sense is saying that we are sort of controlling, again, the discriminator in a specific way that you can sort of link to better numerical success of vacillation GAN compared to the original generative adversarial network. Okay. Now in practice, what do we do? We basically ignore this constraint, let's say, and we're going to solve the min-max task given in equation 13, and we're going to leverage the fact that we must have Lipschitz constant which is less than 1 by sort of incorporating techniques such as weight clipping or introducing gradient penalty. Okay, so again, Lipschitz is essentially describes how large the norm of the gradient is. So if I introduce some gradient penalty in my min-max game, or perform some form of clipping, I'm gonna implicitly ensure that the Lipschitzness constraint is satisfied. All right. So let's therefore summarize the objective for F-GAN training as well as W-GAN training. Okay. So for F-GAN is given in equation 14, and for W-GAN is given in equation 15, and they look almost identical, except that you are essentially kind of getting rid of the differential dual of the convex function F, and you are introducing, as we talked about, gradient penalty. Okay. And as I mentioned, this can be viewed as a reason for a better success, in particular numerical success for vacillation GAN over the original generative adversarial network idea. But what I want to point out more broadly is that both of these problems are in nature min-max optimization problems, which is inherently different than again the problems we talked about in the class so far. So for those problems, we develop all of these fantastic ideas, or talk about all of these effective mechanisms, SGD and its extensions notably, that can find very good solutions, high quality solutions, and also generalize well in a variety of settings, notably when our models are over-parameterized. But when you have a min-max optimization problem, such as these, again motivated by generative modeling, things are not as nice, okay? So in particular, one thing you can do, and it is quite intuitive, is that, well, I have these min-max optimization problems, I have these fantastic tools for minimization tasks that we talked about. We can kind of leverage those tools here, or develop min-max versions of those algorithms, okay? So for instance, you can have min-max version of a stochastic gradient descent, which is kind of called gradient descent ascent, okay? So what's the idea? The idea is that, well, you have two agents. One of them tries to minimize the objective. The other one wants to maximize the objective. Now, we know that gradient points towards the direction of increase. So if you want to minimize, in particular, when you want to train the generator, you perform gradient descent. Okay, so you take the gradient of your objective with respect to x, and then move along its negative direction. But for the discriminator that you want to maximize, use gradient ascent. Okay, so you go from the current discriminator to the next one by following the direction of the gradient, not the negative direction of the gradient. And here the gradient is calculated obviously with respect to y, because we are updating the parameter of the discriminator. Now, it turns out that in a variety of settings, if you use this idea, it's not gonna work. In particular, training GANs is very, very difficult in practice, given numerical instabilities and also what we call the mode collapse, where the generator cannot generate meaningful, let's say, images. So here I'm showing two sets of such results from the literature, where, for instance, in the first case, the target is to generate digits. Okay, so and as you can see, when you train the generator, the images that are generated are not meaningful. They don't represent the target well. So this basically is saying that it is difficult to find the equilibrium. Remember, we said that if we are at the equilibrium, things are very nice. Generator is very powerful, and the discriminator cannot distinguish real and real and fake images. Okay, given that the generator is able to perfectly learn the underlying data distribution. But reaching that equilibrium is not going to be an easy task, especially for naive optimization algorithms, such as the min-max version of SGD. Okay. In the second example, the target is basically a mixture of Gaussians. Okay. And in this case, what was observed was that as you basically train the generator and the discriminator, the generator learns one of these components essentially, or learns to sample one of these components. Okay. So at time 10, let's say it samples from component 1. Time 15K is going to sample from the second component, from the third component, and so on. So it is kind of, again, it is not able to capture the underlying distribution. It captures different components, but not at the same time. So therefore, again, the samples that we are generating are not necessarily samples that represent the underlying distribution that we want to learn. Okay. So again, this can be associated with the fact that it is not easy to reach the equilibrium and have the best generator that fools the discriminator. So therefore, a natural question, and a very important one, is how we can address this issue. Okay, and in particular, are there ways and principal ways to modify simple algorithms such as stochastic gradient descent to make sure that we can reach the equilibrium. Okay, and this is something that we're going to talk about in the next part of this lecture. I'll see you there.